Welcome to convolutions. So recall the convolution of f and g is, we denote it with f asterisk g of t, and this is equal to the definite integral from 0 to t of f of tau times g of t minus tau d tau. And furthermore, the Laplace transform of the convolution of f and g is equal to capital F of s times capital G of s, where f of s is the Laplace transform of f of t, and G of s is the Laplace transform of G of t. So there are a few things that we can do with convolutions. The first thing we're going to look at is just taking the Laplace transform of a convolution. So let's go ahead and take the Laplace transform of the definite integral from 0 to t of sine of tau times e to the 2 times t minus tau d tau. So just note this is equal to the convolution of f and g, where f of t is sine of t and g of t is e to the 2t. Right, e to the 2, then in parentheses t minus tau, that is precisely g of t minus tau. So we have our convolution. So the Laplace transform of the definite integral from 0 to t of sine of tau times e to the 2 times t minus tau d tau. This is the same thing as taking the Laplace transform of the convolution of f and g. And that we can simply do the Laplace transform of f, so capital F of s times capital G of s. The Laplace transform of sine of t is simply 1 over s squared plus 1. The Laplace transform of e to the 2t is 1 over s minus 2. And so that is our Laplace transform of the definite integral from 0 to t of sine of tau times e to the 2 t minus tau times d tau. So this is how we can go about taking the Laplace transform of a convolution. We can also use the Laplace transform to simplify and evaluate convolution integrals. So let's say that we have h of t is equal to the definite integral from 0 to t of t minus tau to the 9th times tau to the 15th d tau. Note this is equal to the convolution of f and g, where f of t is t to the 15th and g of t is t to the 9th. Again, g of t minus tau would therefore be that t minus tau to the 9th. So we can go ahead and take the Laplace transform we have the Laplace transform of h of t, or capital H of s, is equal to the Laplace transform of the convolution of f and g, which should be capital F of s times capital G of s. That Laplace transform of t to the 15th is 15 factorial divided by s to the 15 plus 1, or s to the 16th. Laplace transform of t to the 9th is 9 factorial divided by s to the 9 plus 1, or s to the 10th. So we are looking at h of s is equal to 15 factorial times 9 factorial all over s to the 16th times s to the 20th would be, sorry, s to the 16th times s to the 10th would be s to the 26th. Now we can go ahead and take the inverse Laplace transform to find h of t. So take the inverse Laplace transform. And we get h of t is equal to the inverse Laplace transform of h of s, which is equal to the inverse Laplace transform. We have 15 factorial times 9 factorial. We would need a 25 factorial in our numerator. So we're going to go ahead and divide by 25 factorial out front. And then the bottom is s to the 25 plus 1, exponent 25 plus 1. That 25 factorial over s to the 25 plus 1 is the Laplace transform of t to the 5th. And so we went, sorry, t to the 25th. So we wind up with 15 factorial times 9 factorial divided by 25 factorial times t to the 25th. So we could obviously evaluate the definite integral from 0 to t of t minus tau to the 9th times tau to the 15th d tau. We could evaluate that by hand. We could multiply out that t minus tau to the 9th and then go ahead and take the definite integral that way. Or we can use this Laplace transform, inverse Laplace transform to avoid doing all of that algebra. One last use, we can solve these special equations where we have y of t equal to some function plus a convolution involving y of t. And so note that this is y of t. So the example we have here, y of t is equal to t plus 4 times the definite integral from 0 to t of e to the negative 4 times t minus tau times y of tau d tau. So y of t is equal to t plus the convolution of f and g, where f of t is 4 e to the negative 4t, and g of t is just y, or y of t. And so we have a convolution. So if we take the Laplace transform, taking the Laplace transform will essentially allow us to pull that y out of the convolution. And then we can do the inverse Laplace transform to get back to y. So taking the Laplace transform, we have capital Y of s is equal to the Laplace transform of t, which is 1 over s squared, plus the Laplace transform of f convolution g. So we're looking at capital Y of s is equal to 1 over s squared plus capital F of s times capital G of s. F of s was 4 e to the negative 4t, so capital F of s would just be 4 over s plus 4. So we have capital Y of s is equal to 1 over s squared plus 4 over s plus 4 times g of t was just y of t, so capital G of s is just y of s. Rearranging this becomes 1 minus 4 over s plus 4, all multiplying y of s is equal to 1 over s squared That 1 minus 4 over s plus 4 just becomes s over s plus 4 times capital Y of s equals 1 over s squared. So we get our capital Y of s is s plus 4 over s cubed, multiplying by s plus 4 over s, or capital Y of s is 1 over s squared plus 4 over s cubed. From here, we can then take the inverse Laplace transform to find y of t. So we have y of t is equal to the inverse Laplace transform of 1 over s squared plus 4 over s cubed. 1 over s squared is in proper format. This is the inverse Laplace transform of 1 factorial over s to the 1 plus 1. 4 over s cubed is not quite in proper format. This is 2 times 2 factorial over s to the 2 plus 1. Taking both those inverse Laplace transforms, that 1 factorial over s to the 1 plus 1 is just t. And the 2 times 2 factorial over s squared, 2 times 2 factorial over s to the 2 plus 1 is just 2 times t squared. So we have y of t is equal to t plus 2 times t squared. We essentially were able to pull our y of t outside of our convolution interval so that we could actually solve for y. This particular type of equation has a specific name to it. So this particular type of equation of the form, so equations of the form y of t is equal to some function f of t plus a definite integral from 0 to t of some k of t minus tau times y of tau d tau. These equations are called Volterra integral equations. So equations of the form y of t equals f of t plus indefinite integral from 0 to t of k times t minus tau, or k of t minus tau times y of tau d tau. These are Volterra integral equations. They can alternatively be written as so they can also be written, I can spell also. They can also be written as y of t is equal to f of t plus the convolution of k and y evaluated at t. So if we have an equation of this form, we can use the Laplace transform and inverse Laplace transform to actually solve for that y of t.